I'm not starting, I'm just writing something down for it.
Paper
No.
I think is by Conway, and it's like one page, and it's literally just here. There's the title.
Triangle?
Yeah,
Triangle.
there's the title, the whole content.
Is it just like a counterexample
Well, it's
to
like yes, and then it's a picture of a triangle.
how'd that get published?
I don't know.
Some editor is like elegance, mathematical elegance, the short.
Start a journal in order to publish your own papers like that.
Your own nonsense papers. Well,
Bribe the editor or something like that.
in the first year office, we were talking about how Archive actually does an April Fool's Day thing every year where people just write the most ridiculous papers
Oh, interesting.
for submission. All right, so it's officially 2 o'clock. Are we going to start, or should we wait for some people?
Here, I can introduce you. I would also write your title as well.
Oh,
Maybe
yes,
should
we
we
should do
wait another minute or so? I think that's that needs to be here.
Yeah, please. Go find out.
Is that the milkshake thing?
Oh yeah, I already told you about my milkshake spiel. So this will be fun. I promise they are pertinent to the discussion.
Whole paper.
Like the title's a question. The paper is the word yes with a picture of the answer.
Basically. Nice. And there's 2 authors on it.
Speaking of the milkshake analogy, which I'll get to in a moment, that one is not mine devising. It comes from a book called Shape by Jordan Ellenberg, not to be confused with Eilenberg. It's basically like a sort of recreational math sort of thing about where geometry shows up in the crazy places. So I have him to thank for that illustration.
All right. Very excited board.
You should be very afraid.
That's why I'm sitting back here.
And
I'm glad you're taking the proper precautions.
with that, let's go ahead and get started. We have Merrick here today. We'll be speaking about homology, chain complexes, and
Crazy straws.
Should be good.
Crazy straws?
You'll find out in a moment.
Oh, I know what you're gonna do.
Oh, great.
Over a field, there are crazy straws.
Are there?
They're only over a field, right? You could think of it.
I will say I'm not picking up what you're laying down there.
Okay, never mind.
It's okay. I'd love to hear more about this later, though. That sounds awesome. Okay. Are there any
My
other?
straws are not as crazy as your straws.
I guess find out. I do have some very crazy straws.
Very straight. Very crazy.
Are there any questions, comments, concerns, or even regrets before we begin? No, I wasn't asking here. All right, then let's begin. So, generally, when you ask a topologist for what homology is and to explain it to you as if you're 5, the go-to explanation will be that homology counts the number of holes that something has. Only the problem with this explanation, as the internet so recently shown, is that people can't really agree on what holes are. Recall a few years ago when people were arguing all over Facebook, Twitter, and every social media platform over how many holes a straw has. It's an understandable sort of confusion. I mean, like, when you draw a straw, it looks like there could be 2 openings, or if you consider the hole to be the path through it, then there's just 1 hole. And so the topologist's answer is, look, this space is homeomorphic to this annulus, which has 1 hole. Or you can say, if you squish along it and down to 1 dimension, you end up with a circle, which also has 1 hole. So clearly, a straw has just 1 hole. Only I don't think this is really a sufficient explanation, because if it's only 1 hole, which hole is it? Is it this one? Is it this one? And if you use the explanation of it's the space in between, we kind of lose that with the annulus here, because it's 1-dimensional. There is no space in between. It's 0-dimensional. It's a flat in there. So the argument that I'm going to give, and the one that Ellenberg proposed, is that a straw really does have two holes, but they are the same hole. Here's the idea, is that imagine you take your straw and you start drinking a milkshake. We'll pretend it's a strawberry milkshake. The amount of milkshake coming in has to equal the amount of milkshake coming out by the conservation of milkshake law. It's a very legit physics property. And the same thing sort of happens in this one-dimensional case where or not one-dimensional, but the flat case, where since there's really no difference between the opening and the exit, it's just like a net flow of 0 throughout the whole thing. So this is M1 for milkshake 1, milkshake 2. The conservation law between these is that these must equal 0. So in a weird sort of sense, you can add the holes in an object. And this gets even interesting too when we consider more exotic shapes. And by exotic, I mean pants. You could ask the same question about how many holes does a pair of pants have? Once again, the topology explanation is that a pair of pants has 2 holes, but again, I ask which holes are they? So let's imagine that we have a crazy straw in the shape of pants and attempt to drink through the pants. Then the amount of milkshake coming in the 2 legs equals the total amount of milkshake coming out the waist. And likewise, if you dip one leg in the milkshake and the waist in the milkshake and then drink out of that one leg, you still have the sum of all of the milkshake flowing through comes out to 0. And this also gets more fun whenever we think about this in the flat case as well. Where once again, the net flow through these 2 things is 0. This also gives a better idea of what the holes actually are, because we're not sure whether these openings are the legs or the waist. But one thing that we do know is that these circles correspond to some part of the pants. And by the holes, we mean the boundaries that don't enclose anything else. So for our purposes, a hole is a boundary that is not a boundary of anything else. Which sounds really weird linguistically, but it'll make more sense mathematically when we try some examples. Are there any questions so far?
Is that the crazy straws?
That is the crazy straw. We're going to look at some more crazy straws as we start building up this theory. I'm going to go ahead and erase the board and we'll actually do some homology.
The pair of pants of straw. If you don't do glasses, they combine the drinks, if you want.
I would love it if there was like
That's
a...
the straw that says spaghetti and dogs.
Also in one glass, something else in another glass, lemonade and next to
Perfect.
So just for the purposes of the conversation, I will no longer be calling these topological spaces. Instead, they're crazy straws. So let's say we have the following crazy straw. Just to label these, we'll call this X and Y, or you can think of these as like the openings of our straw. And let's also label these edges and give them an orientation, because why not?
Sorry, X and Y are the openings, or the 3 in between?
Ah, yes, good question. It appears as if my theory is breaking down a little bit. So let's just go with the typical conventions of calling these vertices, and then the A, B, C, D are edges. But we're going to use these the reason why I call them openings is I want to imagine you're trying to stick your mouth on the X point and trying to drink through the Y point.
Okay, so mouth on the, okay,
Yeah, just imagine what's going on here.
sure.
And now I have a very dumb straw if it only worked one direction. So we're going to say that it doesn't really which end that you drink through. So if the flow of the milkshake goes through A and B, it's the same thing. A, the inverse is going to be the same thing as, going through. It's going to commute, is the thing that's going to be nice. And so since we're letting this be commutative, we'll just switch to additive notation to really encapsulate that idea. So to get rid of this ugliness, we'll instead say A minus B, which is of course the same thing as negative B plus A. This of course refers to how the milkshake is flowing through. And we could also ask ourselves the different volumes of it. Maybe we have, 3 milliliters of milkshake coming through A and only 2 coming through B.
Would that work with the identification of A and B that you've done there? Or no, A and B are separate.
Yeah, this is
Okay.
just me illustrating that this is commutative because straws work both ways. And so the idea is that we can have various different combinations of these things. So the entire flow through the milkshake, the entire flow of the milkshake through the straw can be expressed as this linear combination MA plus NB plus KC plus LD. And so what I want to know is, when is the milkshake made a complete flow through the straw? Like if one particle of milkshake comes through, how do we know it's left the straw? Well, it means that the number of times it's come in and passed through Y also has to equal the number of times it goes to X. Like it has to enter and exit the same amount of times, you know. And so we want this linear combination to come out to 0. Kind of like what we saw before by the conservation. This is basically just the conservation of milkshake law. The sum of all of the flow has to come out to 0. And so now that we look at this, we see two big insights that holes form this additive group. And so let's look at how these pieces work together. I'm going to drop some of the analogies now and just look at the math. So let's look at the 0-dimensional components of this graph, which are just X and Y. We'll say that they form their own abelian group. We'll call it C0 for the 0-dimensional parts. And it's the free abelian group generated by X and Y. And we'll take C1 to be the 1-dimensional components generated by A, B, C, and D. And now I want to explain this flow as sort of a homomorphism between the two. 0, which for the moment speaking, we'll just call that del. We'll get rid of the subject for now. Del is a homomorphism. And the way that we're going to do this is that we're going to send A, B, C, and D to Y minus X. Intuitively, we're taking all the parts of the flow and sending them to this path from Y to X. We want to consider all of the paths between those 2 points. The kernel of this homomorphism is going to be generated by A minus B, B minus C, and C minus D. The way that we can sort of check that is, when we carry this through, we're only concerned with this linear combination here. And so we're just kind of looking at all pairs for which n plus ky minus m plus n x 0. And this really only happens if all of these are 0. This is just something you can check by Ripper combination. That this really does span all those different combinations. What you might notice is that the kernel has, that's supposed to be a paint bracket. The kernel has 3 elements in it. It's 3 elements that, in its basis, I mean. And this thing has 3 holes. So there's some sort of relationship between the kernel of this homomorphism and the number of holes an object has. Question so far before we get into the nuance a little bit. Okay, great. So what I'm going to do is I'm going to make this a bit more complicated, and instead of just having these 1-dimensional components, I'm going to throw in some 2D stuff here. So let's fill in the space between A and B with a 2 cell. We'll call it capital A, because we're original with our notation. And this kind of closes up the gap between A and B. And so if our theory is really working nicely, then this would get rid of the number of holes in our calculation. So let's experiment with this some more. So now we have a 2-dimensional component index. We have 0 dimensions, we have 1 dimensions, now we have 2 dimensions. So C2 is the free abelian group generated by A. And now we want a homomorphism from C2 to C1 and a homomorphism from C1 to C0. And now, previously what we did is that we sent every one of these to their boundary, y minus x. And if we're extending this theory, we should do the same thing here. We should send A to its boundary, which A's boundary, we'll assume A is oriented, that was clockwise, A minus B. So this homomorphism we call D2, this one del1. This one sends A to A minus B, and this one, as before, sends A, B, C, D over to y minus x. But what we've sort of done here in this map is that we've kind of gotten rid of this A minus B hole, because we're sending A to its boundary, and then now we're sending things to their boundary. The composition of these homomorphisms results in this net result. What am I saying here? Okay, let me take a step back. So the image of del2 is equal to A minus B. And the point is we like to get rid of sort of redundancies that we have here because A and B no longer enclose a hole. And in fact, also this means that A and B are kind of the same because we kind of humped up them from one to the other by moving along A. So to get rid of these redundancies, we do what you normally do in algebra. To get rid of redundancies, you take some sort of quotient. So we take the kernel of this guy and mod out by the image of this previous one. So we end up with this group, kernel del1 divided by image del2. And that's what we want now. This resulting guy is A minus C, C, 1 generated by B. This gives you now B minus C. Now there's only 2 elements that in that basis, which accounts for the fact that this thing now has 2 holes. And the other advantage of this system is that it gives us not only different ways to count the number of holes, but it allows us to classify different types of holes. I'm going to erase things here so my next drawing is a bit more clear. So we have, I'm going to stretch 2 different, let's imagine there's a 3-dimensional thing living here. So instead of stretching just one 2-dimensional component, we're going to stretch one from A to B and another one from B to A. So we have this sort of little croissant-shaped sort of thing, where on the front this is A, and on the back this is B. And we'll assume that the opposite orientations for reasons that'll make sense in a moment. Well, I guess it makes sense now because A, we said went from A to B, and so if we want things to connect with it, we'll say that B into A. So they're backwards orientations of each other. And so let's look what this does. C2, instead of being generated by one thing, is it okay if I write this part right here? Okay. That's now generated by 2 things. It's generated by A and B. And so now we map A and B to A minus B by del2. And we map everything as before, A, B, C, D, down to y minus x as before. And this gives us a different picture than we had earlier. Yes?
I have a question. Why is B not mapping to B minus A?
Why is that? I'm not entirely sure why I did it that way. I mean, in the end, what I want to get is that the kernel of del2 is generated by A minus B. And I think that has something to do with it. And that really only works if you have it mapped that way. That way, there really are opposites. Or not opposites, but the way this works out that I want it to.
I'm just confused because the like the theory makes sense so far to me.
Mhm.
Like with those all mapping to y minus x because the orientations are all the same. But if you had one where the orientation was flipped, when one like if A was flipped, wouldn't like A map to x minus y?
Oh, I see. I might have also spoken wrong in what I was trying to say earlier, because
Okay.
if A is, oh yeah, so if A is oriented
So are
clockwise,
they
and we
the-
want B to be oriented counterclockwise, so that way they do map to A minus B.
Oh,
Sorry,
okay.
I misspoke earlier.
I think I understand now. So it's
I also mixed up clockwise and counterclockwise.
okay.
There we go.
Okay. I'm gonna choose to think about it as like them being oriented out and versus oriented in. So they're both oriented out. So they're both.
And that's the same idea, like, right-hand rule sort of thing.
I think.
Okay, cool. This thing right here, by the way, I should probably clarify what this is. This is called the first homology group. Let's pretend that we call this space big X. H1 big X is equal to this guy. And we can do something a little bit different too, where H2 is going to be the kernel of D2 over the image of del3. What's del3? I haven't defined that yet. But the thing is, there are no three-dimensional components, so the image here is just going to be the image of del3, whatever it is just going to be trivial because there are no three-dimensional pieces. And so we end up with this, and so this one is isomorphic to Z2 plus Z2. This one is going to be isomorphic to just Z. So we have these sort of two one-dimensional holes and one two-dimensional hole. And so that's the other power of homology, is that not only do we see what the holes are, but we're able to classify two different ones. There's a hole here that's one-dimensional, here, and there's also this chasm inside our croissant. That's fundamentally kind of different. Of course, though, this is not as clean for more general spaces, and so we're going to look at some tools for how we actually compute these things. It's not always as nice as looking at these individual pieces. Are there questions before we transition to that part of the talk? Great, okay. So before we can get to how these things are computed, we'll need to talk a little bit about simplicial complexes. Or actually, I'll talk about something even better than simplicial complexes, delta complexes. Essentially what we're going to do next is that we're going to break down spaces into triangular pieces, which those are usually nice to work with. And so since we can do nice computations like what we just did on triangle-like things very well, this makes it a nice way to compute these homology groups for spaces in general. So first, an n-simplex is just a collection of n+1 points that are geometrically independent. And what we mean by that is that they don't all, if you are living in n-dimensional space, the points don't lie in a space that's dimension less than n. Or sorry, is it n+1 dimensional space? No, that's right, yeah, you don't want them all less. So if you're living in 3 space, you don't want all your points being coplanar, because then they lie in a triangle and not a tetrahedron like you'd really want. We always want it to match up the nice thing for that dimension. And so these complexes, as many are familiar, look at things like the 0 simplex is the point, the 1 simplex is the line, the 2 simplex is the triangle with the space filled in, and the 3 simplex is the tetrahedron, once again with this void filled in. You could also think of it as the smallest convex set in Euclidean space that contains all n+1 of these points. And of these ways to characterize it, there's a sort of standard representation for them. So the standard simplex, which we'll call delta n, is as follows. And these points right here are called the barycentric coordinates. And we also, this also has special subparts of it. So let's imagine that we have the points, let's say this is made up of the points v0, v1, all the way to vn. These all live in n plus 1 dimensional space. And we want an ordering on them because just like we had orientation on those lines earlier, we want to keep an ordering here that allow us to keep those groups. What happens when we say delete a point? Well, then that gives us an n-1 simplex. And so this resulting n-1 simplex is called the face. And when you take the union over all the faces, you get the boundary. So for example, if I were to take this tetrahedron and then remove a point, the set spanning the remaining vertices is just that triangle. And then likewise, if I remove a different point, like this top one, then I get this bottom triangle. And then I can do that for all of the points, taking one of the points away and then taking that closure. And when we glue them together, we get a tetrahedron, but now it doesn't have that filling inside, it's empty inside. And so that's why this is a reasonable definition for the boundary. We also abbreviate the boundary as del delta n. And then since we have a boundary, we'll also be talking about the interior, which will, the interior is also known as like the open simplex. So there we put a circle on top, and that's just equal to the simplex minus its boundary. And so that's just the jelly filling of our weird triangular donut. And now that we have this, we can define what's called a delta complex structure. Normally what you do with simplicial homology is that you'd be defining them in terms of simplices, and so you take your space and then just try to find a way to fit triangles, tetrahedrons, and lines to them. And that works, certainly, but it's computation is not always the nicest to do. Like to do this for the torus, you do like 14 triangles, I think, with 11 edges, and I forget how many vertices. But we'll see in a moment that the work becomes a whole lot easier when we consider this more general structure. The delta complex structure is kind of like a happy marriage between simplicial complexes and CW complex structures. So by a delta complex structure, we mean a collection of maps which we'll call sigma sub alpha from delta n to x. The alpha depends on n, by the way, such that the following conditions hold. First is that when we restrict ourselves to the interior, this map is 1 to 1, and each x corresponds to 1 sigma alpha. We don't want to, like, if we pull back next, we don't want to land in multiple of these different maps. We just want it to correspond to just one. When we restrict ourselves to a face, on the other hand, we want to say that that's sort of the same thing as this map where we're restricted to an n-1, the same kind of map but with an n-1 simplex. This is so that we preserve the structure of the boundary. If we have a certain orientation of our vertices over here, we don't want that to be messed up whenever we're mapping to our new shape. And then lastly, just because this is topology and we love our open sets, a subset A in X is open if and only if the pullback of A is open for all alpha. Some of the keen-eyed among you might notice, Merrick, that's just a CW complex structure. It is. It's just we're restricting ourselves to triangles instead of just those cells as before. Questions? So what do we do with these things? Well, what we can do is that we can take sort of these components and form ourselves an abelian group, which we'll call del sub n of x, where x is our space in question. And this is just the group generated by the n simplicities of x. The elements of this group are called the n chains, which we'll see how those come into play with chain complexes. And now, how do we use these chains to compute these groups? Or, yeah, the groups, that's what I'm talking about. We do that as follows. As we saw before, we are trying to send our n simplices to their boundaries by some homomorphism. That's what we want. So we want a given map that does this for us, and so the map that we're going to use is this one. We'll call it del sub n sigma alpha is equal to sum over I negative 1 to I alpha restricted to not I hat n. What's the hat about? Well, remember earlier the thing where I said you can remove a vertex and then you have that remaining face left? And that's basically how you get the boundaries, by looking at those faces. To remind ourselves that we're taking a vertex away, we put our hat over the ith component to remind us to take away that component. This just makes it notationally nice to talk about. As for why that -1 is there, here's a good way to think about why. And this kind of goes back to the question Leslie was asking earlier. Why are we assigning the orientations the way we are? Okay, so we want an orientation on all of these sort of simplicities that's sort of nice and consistent. And so we want our boundary homomorphism on these to send them to that. The way that we can think about this is that, I guess the one-dimensional case is not entirely clear what's going on here. We want this to be v1 minus, I guess that one you can think of like, you know, your source and your sink. You want the end minus the first. As for the two-dimensional case, that's where things get interesting. The boundary homomorphism is going to give us v1, v2 minus v0, 2 plus v0, 1. Let's imagine traversing this path. So when we go from v1 to v2, we're going with the flow. But when we're going from v0 to v2, we have to go against that arrow. So we subtract that part. And like when we're going from v0 to v1, we're going with the flow here. And the same thing is true for this tetrahedron, where the boundary homomorphism will send things to v1, v2, v minus v0, v2, 3 plus v0, v1, 3 minus v0, 1, v2. This alternating sum just gives us, because these are like really nice orientations for all these shapes, and so in order to give us this nice orientation, we define it this way to give us this cool alternating sum. Questions so far? Now that the groundwork has been laid, we can actually use this tool to compute the homology groups of different shapes. I just realized the purple doesn't show up very well for distance. My apologies.
Yeah, you can turn on the light.
Ah, there's a light. I am what scientists call a goofball. I apologize for my odd outbursts. So, let's start with everyone's favorite shape, S1. So, I'm going to pick for myself a delta complex structure that works nicely. And so, what better than just a point with a line? Here's a zero-dimensional component and our one-dimensional component, and then I'll call that zero-dimensional component B, and the one-dimensional component E. Now we go ahead and look at the groups generated by these. So, C0 is the group generated by that vertex, and that's just isomorphic to the integers. C1 is group generated by E, and that's isomorphic also to the integers. And then for, maybe I'm going to change notation here. That's right, I said these were delta n's. So there we go, that's a good point. Delta n greater than or equal to 2. Well, there are no components for 2 or bigger, and so this is generated by the empty set, which is just a trivial group. So let's go and look at how these maps behave. We want a boundary homomorphism delta 2 over delta 1. I'm just going to not put the S1 here just because I'm a little lazy, but it's understood what I meant, right? Now let's pause and admire these maps here for a moment. If you go back to the definition for the way that we define those del n's, you can check by a brute force computation that del n composed with del n plus 1 is always equal to 0, which means that the image of del n plus 1 is contained in the kernel of del n. And so our quotient that we're chasing, kernel del n over image of del n plus 1, is well defined. And these also happen to be abelian groups. And so anytime you have these sort of chain of abelian groups where their pairwise compositions come up to 0 or consecutive compositions come up to 0, this is what's known as a chain complex. Whoa, we said the title. Okay.
Roll credits.
Roll credits. that's right. Hishy. Okay. So now that we have these things in play, let's go ahead and look at these. So let's kind of start from the basement and move upwards. Del 0 is just a map from delta 0 to 0. That's just a 0 map, and so its image is 0 and the kernel. Well, this we already said is Z, so it's Z. And for del 1, the image is also 0 and the kernel is Z. For del 2, and really above actually, we'll see that the image, wow, why did I put that? That's supposed to be a Z. Great going. It's 0 and the kernel is also 0. Because it's a trivial group. So this gives us our zeroth homology, which is going to be your kernel of del 0 over the image of del 1. Well, the kernel is Z, modded up by 0, it's just Z. H1 is the kernel of del 1 over the image of del 2, which is going to once again be Z over 0. And for anything higher than that, we get 0 modded by 0, it's just going to count to 0. And so these are our different homology groups for the and 2 and beyond, really. We'll do this sort of thing. Pay special attention to the fact, by the way, that this is also the same fundamental group we get. Keep that in the back of your mind for later. That the first homology is equal to the fundamental group in this case. Questions about this first example?
Is that formula there, kernel del n mod image del n this one.
Ah, yes, that
That's-
formula. That's the thing of being important. Because, so, I'll do green. This is the nth homology group vector space. Is that. It's the kernel Dylan plotted out by the image Dylan, this one. Thank you. Let's try a more fun example, like the torus. So like I said before, the torus, if you were going to do that with the usual way you play in simplicial homology, you have to triangulate the whole thing, which requires you to have around 14 triangles. But the advantage of delta complexes is that we only need the pieces to be homeomorphic to our end result. So we can just look at the fundamental polygon for the torus. And then put an extra line in it, so that way it actually is made up of triangles. A, C, T2. And then, because we need to label all of our regions, and we do have two-dimensional parts to it, we'll call this part U for the upper triangle, and this part L for the lower triangle. And so we have, once again, C0 is, oh, and these vertices all get identified in the quotient. So that one's B, that one's B, that one's B, we're all B. One is generated by C by L. And so those are the different groups we get. I did it again. Those must be triangles. If I'm going to be consistent with my notation. And so, let's go to look at how these maps behave. So, del 0, that one has an image of 0 and a kernel of z. For del 1, that one has an image of 0 and its kernel is that z cubed, which I'll be using to refer to this thing. And del 2 has an image, I guess I should say these are isomorphisms. There we go. And the image of this one is isomorphic to z, and the kernel is also isomorphic to z. Are there any questions about how we got to those individual kernels and images, by the way? Essentially what you're kind of checking for is you're kind of using the intuition that I talked about earlier, that your holes are boundaries of things that aren't boundaries of anything else. So what you kind of do is kind of chase these diagrams around to see how they're built up. Like for example, one of the ways that we can check that the kernel of del 2 really is equal to z is that when you look at this homomorphism, this is a generic element of this guy. And we're wanting to send that to some combination of E plus Q of A plus B minus C. Why are we doing that? Well, because L, the way that you get that is A plus C, or A, slow down, A minus C plus B. And same thing for you also get A plus B minus C. They have that same sort of boundary piece there. And so we're looking for what makes this equal to 0 to get the kernel. And well, you realize that really can only happen if Q equals negative P. In other words, the kernel of this del 2 is going to be generated by U minus L, which is in fact isomorphic to Z. And it's kind of looking at how each piece is connected to its lower dimensional boundary. And so using these things, let's go ahead and figure out the corresponding homology groups. So H0 is going to be the kernel of del 1 over the image of del 0, which is going to be isomorphic to Z. H1 is going to be kernel of D2 modded out by the image Did I write down D3? Nope, that's supposed to be D1. Kernel D2, sorry. Did I get this backwards? Yeah, I'm writing it backwards. That's D0, D1. There we go. Kernel D1, D2, which is going to be C cubed mod by Z. It's isomorphic. That also looks familiar. And then I don't have the three-dimensional pieces counted out, but you will see that since there's no three-dimensional pieces, then the kernel of D3 is going to just be 0, and so you'll see that the second homology group is just going to come out to be the trivial group. I think. Did I get that wrong? I might have. Don't quote me on that. I didn't write that down.
The second homology group is the kernel of D2 on the image of D3.
Oh, okay, yeah, so it's 2.
And you have the kernel of D2 over there. And then D3 is 0, so its image
Is, yeah, the kernel of D2, which is Z. Okay, yeah. I was thinking of H3 and above. There we go. So this one's Z. Okay. That's the idea, that you can compute these higher orders relatively simply, which is the big advantage that homology groups have over the fundamental group, because for higher order fundamental groups, those are notoriously difficult to compute. But these, if you can just think about these things algebraically and draw some pictures, you have a nice way to get these groups.
What do we draw the answers that we're getting for these homology groups?
How will we draw them?
Yeah, I mean, is this just like some abelian groups? Or can we picture in our minds the answers that you're computing in some fashion? Is it clear that there is a way to geometrically understand what C plus C means for H1?
Let's see. So I don't know for certain off the top of my head, but I have a guess as for how this is working. Because if we call back to what these are, how we're computing these, is that we're looking at these kind of chains of these pieces fitting together. And so for H1, we're looking at, if we actually glue this thing together and get our torus. A will be over here, and C will be this green line. And so my guess is that it'll look like different combinations of how we can traverse these different edges. And likewise for the two B's, it'll look at how you traverse those two-dimensional pieces.
So do you have, so for example, when you compute an H1, Z3, there, mod Z, so Z to the power of 3, that's 3 different things you can see in this picture. In fact, you may have just drawn them with the torus, right?
Yes.
And then what are you modding out by? What's that Z that you're modding out by in terms of these generators?
Oh, okay.
Think of it in some fashion in terms of.
So I think this comes back to that intuitive explanations for holes that I gave earlier, that holes are boundaries of the shape that aren't boundaries of anything else. And so when we look at these, two of these ones, like particularly the red one and the blue one, is that the one I want to talk about? I think so, yeah, so you pull that blue one tight and it eventually comes to the center of the donut where it bounds something, but there's nothing there. And likewise, that red one, it bounds the empty space inside the torus. So they're boundaries that aren't boundaries of anything else. The green line, on the other hand, it can't really be shrunk to one of those two. It's a boundary that does bound something else in the shape. And so by modding out, we're getting rid of the things.
So what's the generator of Z should be something like C minus A plus B?
I believe so. In fact, I think that's exactly what it is mentioned in Hatcher.
You have the relation up there.
I have the relation up here. Oh yeah, there we go.
Yeah, so if C minus A plus B is equal to 0, which is what you're modding out by, that says that C is equal to A plus B,
Yes.
right? C is your green curve. And then the other two curves in your picture are A and B.
Yes.
And those are what's left. That's C plus C plus A and B.
Yeah, and then after the
One of the reasons homology is so powerful is because we really are computing things that we can understand geometrically in some fashion. So sorry to interrupt, but I
no, that was great. This definitely helps solidify my understanding, and everyone else's, I'm sure, to try to think about what these things mean.
Is that an annulus down there, or is that
That is a sad torus.
Okay.
It's a little deflated. Yes.
You said this already, but I can't remember the exact definition. So this is a delta complex of a torus, but
Yes.
it's not a simplicial complex. Is it because it's not ejective when you restrict to the like the vertices?
Because the main reason here is that these aren't triangles. The things that they partition out, they're like these little orange slices that you get, minus the orange, just like the peel sort of thing. Whereas for simplicial complexes, they need to be triangles or tetrahedra sort of thing. The main difference is that for delta complexes, they're homeomorphic to something that's triangular. As it turns out, by the way, every delta complex is homeomorphic to a simplicial complex using barycentric subdivision. And so you get the same results.
Like if you wanted to try to form triangles, each of your vertices are the same vertex, so the inclusion wouldn't be
Okay.
negative, which is the.
Oh, yes. Thank you. Any other questions?
Why do you need 14 triangles?
Because Hatcher said so. And I trust that he went the more painstaking way of figuring that out than I did. I think that also has something to do with Euler characteristic as well. Because it creates like a graph on the thing, and so you need the faces minus edges plus vertices to equal a certain number, which I think for the torus is 0. And so there's a certain way that works nice.
So H1 in this case is also pi1.
Yes, and that actually leads me to the last thing I want to address. I mean, I also had stuff prepared to calculate RP2, but we are getting low on time, and so the last thing I want to address, which if you guys still went down for this, we have about 8 minutes. Is it fine if I continue on with this, or should I cut things here for open for questions?
What else is on your list?
The last thing I want to talk about is the relationship between the first homology and the fundamental group.
Oh, that would be great.
Great. As Leslie pointed out, and like I kept subtly hitting to pay attention to, the first homology keeps coming out to equaling the fundamental group. I will say I kind of cheated a little bit. It's not always equal to the fundamental group. We get equality here because in those cases the fundamental group happens to be abelian. If I showed you a more exotic space, like I think it's I don't remember the fundamental group for the Klein bubble, but I don't think it's abelian. Sorry?
It is, but the wedge
Oh,
of
it is.
circles is.
Wedge of two circles. Okay, yes, thank you. That would be one where if you work out the first homology and the fundamental group, you would get two different things. But they are still related. There is a homomorphism H from pi1 of x to h1 of x. And whenever you restrict H to the commutators, group of pi1, when you make this restriction, it turns out to be an isomorphism. And so, in other words, the first homology is the abelianization of the fundamental group. Sorry?
The restriction of the combinator subgroup should go to 0.
Restriction of the commutator subgroup. Oh, I see. Thank you. To go to 0. Why is that H1? And the main thing driving this is that loops also happen to be one-chains. So when we were computing H1, we were looking at all those little one-dimensional components and seeing all sorts of paths that come back to themselves. This is just a loop. And you also see that the way that the fundamental group acts is very similar to how homology groups act. So for instance, I wanted to define a term. So we'll say that F is homologous to G if F minus G is the boundary of some two-chain.
The Klein model thing I was wrong about.
Oh, thank you for clarifying. I almost had an existential crisis. How dare you?
Alright.
And so let's see how that works. For instance, one thing you can check is that the constant map, just the point, that is kind of equivalent to F being homologous to 0. Is that what I want to say? How did I want to say this? Yeah, I wanted to say F homologous to 0. This is just kind of like a weird thing about empty sets that there's nothing in a point, so you can say it's like an empty chain in there. It's kind of a silly one there. But what gets more interesting when you look at the operations here. So, for instance, if F is homotopic to G, then that also does imply that F is homologous for G. So if I have 2 points, and then I have 2 paths connecting them, are F and G, well, because they're homotopic, there's a way to deform this one into that one. And so somewhere along the path, you kind of get this straight line. And if you cross horizon squint, you get something that kind of looks like those squares with 2 triangles put together, where you have your 1 2-chain over here and another 2-chain over here. And so F and G really do bound a 2-chain. And then lastly is that the composition of paths is homologous to the addition of those 2 1 components for a similar reason. So if you have some path going here, and you compose it with another one going here, their path composition is homotopic to this green line. I don't know why I made that the same color. That should be a different color. And so we have here F, G, F dot G, and they all bound a 2-chain, which means that the boundary of S is equal to F plus G minus F post G. And so these 2 are homologous. And that is everything I had prepared to present, and I open the floor to questions. Thank you.
One observation, the statement that any loop can be viewed as an element in homology, and that statement up there that composition corresponds to addition of them.
Mm-hmm.
What does that tell you about that map H?
What does it tell us about the map H?
Yeah. It's like, what kind of map is H?
It's a homomorphism.
Okay, great. And it's anything else?
I believe it's injective, isn't it?
Well, it wouldn't be injective because you have there that it's mapping like a non-trivial subset.
Oh, surjective, sorry.
Great, so it's surjective.
That's all I was saying.
And then if you use the first isomorphism theorem.
Oh yeah, so then pi 1 divided by the kernel of this map gives you H1. The more important result, yes. Let's put that down for good measure. So pi 1 divided by the kernel H isomorphic.
And then the kernel of H has a description in terms of
Sorry?
we know what the kernel is. Do we know what the kernel is?
It's the commutator subgroup of pi 1, right?
That's right. So we know exactly how to express
know, I'd be tempted to wonder that. Like, as I was preparing this presentation, I started thinking, what would it be like to drink through a torus? Like, we're really running with this milkshake analogy. Just like using that quotient map I talked about earlier, where everything goes to B, so you're just like trying to drink through that vertex where everything's identified and seeing how things move through A and B. That's too weird to think about. I'm sorry. If you come up with the Mobius band of a straw, let me know.
It's like a really wide.
Which I guess like you could, like, you know, the infinite Mobius strip sort of thing. Like, so how would that look? Just like if you lengthen a Mobius strip.
It would intersect itself at some point.
For like that net flow analogy, you need to have the concept of like what is incoming and what's outgoing.
Right. So where is the hole in a Mobius strip?
But you could use it as
Mobius spoon.
All right, yeah, let's thank Merrick again.
Thank you guys.